All right, hey everybody, welcome back. In this short video, I want to follow up on a result that I mentioned at the end of last video, but did not explicitly prove. And that is that when I calculate my Maclaurin series for the function e to the x, right? First of all, what I did calculate is that the Maclaurin series has the form sum as n goes from 0 to infinity of 1 over n factorial times x to the n, right? And so we saw that was equal to 1 plus x squared over 2 plus x cubed over 6 plus dot, 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 right? Plus x to the n over n factorial plus, right? And that would go on forever. But what I mentioned out loud and did not explicitly prove is that the radius of convergence is equal to infinity in this case, which means that this Maclaurin series is actually a way to express the function e to the x, and that works for any x value. Even though this is a series centered at 0, this series would be faithful to the original function e to the x, no matter what x value I'm plugging in. And that's a bold statement. I want to explicitly prove that. And the way that we typically calculate radii of convergence is to use one of our series convergence tests. In this case, let's use the ratio test. Right, so by the ratio test, we are going to look at the n plus 1th term, right? So that's, whoops, oh my goodness. Yikes, okay, sorry about that. Let's try that again. By the ratio test, this is going to be equal to, we'll take the n plus 1th term, so that's x to the n plus 1 divided by n plus 1 factorial, and then we will divide that by, right, sort of bigger division, we'll divide that by the nth term, so that's x to the n over n factorial. We'll take the absolute value, and we'll take the limit as n goes to infinity. Figure out what that is. And as we have done for several other examples, we will rewrite this and simplify. So this becomes x to the n plus 1 over x to the n times, and then we'll end up with an n factorial up top and an n plus 1 factorial in the denominator, right? So this is really the limit that we want to compute. Well, that is nothing more. We can simplify that, right? And the x to the n will cancel, leaving us with a single x in the numerator. The n factorial up here will cancel with most of the n plus 1 factorial down here, leaving us a single 1 over n plus 1. And so what we get then is a limit as n goes to infinity of x over n plus 1. Great. And so what does that equal? Well, it's a little weird because there's still an x in there, but I want to point out that for fixed values of x, for fixed x values, that should say fixed right there. For fixed x values, this limit equals 0. Right, so as long as I'm fixing my x value in advance by letting n go to infinity, that expression will ultimately equal 0. So this expression equals 0 for any fixed x value. And by the ratio test, right, the ratio test said that our series would converge as long as that limit was less than 1. So in fact, so this series converges for all x values. Right, and so that's kind of crazy. So even though we are centering our Maclaurin series here at a equals 0, even if I wanted to evaluate, say, e to the 100 and see whether or not this was a good representation at x equals 100, even though 100 is really, really far away from 0, what we would see is that this series would indeed converge to the value of e to the 100. And that would be true, not just for x equals 100, but that would be true for every single x value. Okay, and to help illustrate this, here is our function e to the x, right? That's drawn here in black ink. So that's our function e to the x. And here is at the moment, it's just a linear approximation. So I cannot graph my infinite series here in this program. This is the website Desmos. I cannot graph that in Desmos, but what I can do is I can create a sequence of partial sums, aka a sequence of these Taylor polynomials. And notice that as I add on more and more values, right? So here's x squared over 2. Here's x cubed over 3 factorial, so that's going to be over 6. Here's x to the 4th over 4 factorial, so that's 24. Here's x to the 5th over 5 factorial. And what we see is that our purple Taylor polynomial approximation is actually getting closer and closer and closer to our e to the x function, right? And what we can claim is, based on our work on the previous slide, this will continue, and I will get better and better and better approximations as I go further and further out in my Taylor polynomial approximation. And in the full Taylor series, this would converge exactly to the expression e to the x. Very cool. So that's all I got for you in this video. I will see you all next time.